Assalamualaikum warahmatullahi. Okay. So you guys can hear me? Okay, good. So Assalamualaikum warahmatullahi wabarakatuh and good morning. So today we're going to continue our chapter on Z transform. So this is a part 2 of Z. Okay, so sorry, I'm disconnected just now. Hopefully everybody's still here. Okay. Okay, so let's do some recap first before we continue our chapter on the Z transform. So let's see what we have learned so far. Okay, so this is actually this is a one-page mind mapping of our overall content for this course. So from first week until week 14 later. Okay, so what we have is actually we're going to focus. So mostly because what we do is first week, second week, so it is on the general system. But starting with the third week, so we are starting to focus on what we call the LTI system, so which is a linear and time invariant system. And to have a system, so what is a system? A system, you should have input, you should have output, and you should have your operation. Okay, so inside this green box is your operation. Okay, and because this is a LTI system, so our operation, our system can be represented by two things. One is the equation relating the input and output. So this one, so you have input, output. Then you have an equation, yn equals to xn something. Okay, but we have another option. We can represent our LTI system also with what we call the impulse response. So this is impulse response. We denote our impulse response as a Hn. Okay, so we have two options. One is using that what we call a difference equation, and then another one is using impulse response. So those are the with impulse response. If we have an impulse response, so we can do an operation called convolution. Okay, so you have an input, so you have your filter, which is impulse response, and then do convolution, you will get your outputs. So if you're not using convolution, so because a convolution is, you can do this convolution only for FIR system, finite impulse response. If your filter is, the impulse response is infinite impulse response, you cannot do convolution. So you only have one option, which is to solve the difference equation. For FIR, you have two options, either do the convolution or solve the difference equation. Because what is the LTI system? LTI system can be represented by either difference equation or impulse response. Okay, convolution is only for FIR. And we have seen some analysis. So this is actually the system, the overall system. So to get the output, so actually it's just as easy as you should have the filter, do convolution, you will get your output. You have your input, impulse response, do convolution, get outputs. Okay, but we don't stop there because we have done that. We need to do analysis. Okay, because to understand the filter. So you can do convolution and then you get results. So what is actually happening? So this is where we need to do analysis. And the type of analysis that we have learned so far is actually two things. One is a stability, another one is a causality. Okay, and we have seen this. This is a test on impulse response. Test on impulse response stability. So you do the summation of all values in the impulse response. You should get less than infinity. Then the system is stable. But if you are looking at difference equation, why 2? Because LTI system is represented either by difference equation or impulse response. So that's why we can do tests based on those two. Okay, difference equation, you do the test BIBO test. Causality, the same thing. We can look at our impulse response, which is a HN. So you just check, it's supposed to be 0 for all n less than 0. And if you are looking at the difference equation, you should found no future input or output. Okay, so if there is future or input, future output or input, so then the system is not causal. Okay, so this is, and then what's next? On last Tuesday, so we have done this also, chapter 4, which is a Z plane. So we do Z transform. So already know how to do Z transform. So Z transform is just a summation of your impulse response multiply with Z to the power of minus n. Okay, you do that. And when you do that, actually what you do is solving a geometric series. Okay, so you have seen one video on that one. So basic maths on what is a geometric series. So you have done that. So when it is IIR, infinite impulse response, or infinite geometric series, so you'll find that the results is sometimes you get infinity value, sometimes the result is not infinity. And what we want to know is just which Z will give you infinity, which Z will give you a value which is not infinity. So we have done that. So this is what we call a region of convergence. So we need to know which region or which Z value that will give you a converged value of each Z. Right? So then from there, so we have seen on another test. So we have covered causality, not stability. Stability today. So we have seen on causality. So causality means a right-sided ROC when you have a Z greater than. Okay. So whenever you have the ROC, Z greater than, so it is causal. Whenever you see a Z less than, so then it will not be causal. Okay, so today we're going to look at stability, right? So just to go through fast, so actually later next week we will have an inverse Z transform, and then the week after that, so we will start doing Fourier transform. So this is a discrete version of a Fourier transform. So there's a name, DTFT, discrete time Fourier transform. And then we will go back to Z transform and then see some relationship between Z transform and Fourier transform. Okay, first look at Z transform and then Fourier transform. What is the relationship between the two? And then later more on analysis on the Fourier transform, and then a full version of a full discrete version of Fourier transform. Okay, so we will look this later because the first thing, the TFT is not a full discrete. So we will see something which is a full discrete. And then later we will have, we will cover on how to design the filter, because so far what we do is we just assuming that we have the filter. We do analysis on the filter. Okay, so you have inputs, you have the filter, you know what to do, how to get Yn, which is do the convolution. Or if it is IIR, so you have no option on doing convolution, you should solve the difference equation. Okay, so far we have done that. But on the last 3 weeks, our last 3 weeks, so we will see on how to design the filter. So the filter is not given to you, but we just give you specification that you need to design the filter. So before we can design, we need to understand the filter first. So that's why we have a lot of analysis on it. Okay, before we can do the design. And this is will be very helpful for your assignment. This is a MATLAB code, a MATLAB function relating to all a DSP concept that we have. For example, if you have a signal, how to plot? So you use plot. So there's a function plot. How to do convolution? You use the CONV. See, this is a CONV HX. So H is the impulse response, X is your input. But if your impulse response is IIR, infinite impulse response, so you cannot do convolution. So what is the option? Do this difference equation, solve this. So how to do that? You should use function filter. Okay, so where now you are having B and A. So what is H? H is actually B. If you look here, impulse response, Hn, the filter coefficient B. So that one is for FIR. Okay, so this one you can just replace with B. H is actually equals to B for FIR. Okay, so we already know that. So in your assignment, you will need to learn this on yourself. Okay, so you should try that. Okay, so those are about the assignment. Okay, so any question before we continue? That's a little bit of a recap. Okay, so this is what we have seen, Z transform. So this is the equation. So we already know this. So what we need to do is just a summation of our impulse response multiplied with Z to the power of minus n. And then we have seen some example. So this is one of the examples. So what is the Hn in this case? In this case, the H is alpha n un. So this is IIR, infinite impulse response. And then we have seen about causality. Okay, so there's a few examples on this causality. So in this example, where the Hn is equals to alpha n un, so we will get the ROC greater than A. An, un, so the ROC is Z greater than A. So when it is a greater, so you should have a causal system. And we have seen this example also, so where you will get the Z less than. So this is showing that this is actually a non-causal system. Same thing here, so we have two terms. So one is a 0.5 n un, the other one is a 2 to the power of n, u minus n minus 1. Okay, after you do the solve that for hz, so what will you get is a 2 ROC. So the first one is a z greater than. This is causal. But then you have another one. So because we have two terms here. So but the other one, so this is actually 0.5 less than. Oh, sorry, not this one. Is it a z less than 2? Okay. So this is a mix. So that's why we get a ring shape of the ROC. So because we have this less than, so then this system becomes non-causal, even though we have greater than. So but it is a mix of a greater than and less than. So whenever you have a less than, it becomes a non-causal because you have two terms here. Okay. All right. So let's look another example, which is now this example. So we are still looking at causality. Hn equals to 1111. So what is this? Is this FIR or IIR? Is it mentioned somewhere here? Okay, no. Okay. So what do you think?
Seems to be an IIR.
IIR?
Yeah. FIR. Sorry.
FIR? This is FIR. Okay, so how to know that? So what is F and I? F is finite. I is infinite. What is finite? Finite is the length of the signal or the length of this sequence is not equal to infinity. So if you can count 1, 2, 3, 4, means that obviously that one is finite. If you cannot count, means that if you count, it goes to infinity, then that one is infinite length. So finite impulse response and infinite impulse response is actually referring to the length of the sequence. Okay, so all right, so this is before because previously we have seen 3 examples on IIR. So let's see one example on FIR. This is an arrow. So sometimes we put it an arrow, sometimes we don't put anything. Sometimes we put an underscore, a line, underline. Okay, here. So same thing. So we put it into our equation, which is the summation. It starts with index 0, 1, 2, up to 3. So 0 up to 3. Hn multiply with z to the power of minus n. Okay, so expand this, expand. And because Hn is everything 1, 1, 1, 1, so then we can just remove that one. Okay, you can just remove that because that one is actually a 1. So this is after you simplify, you can get n from 0 up to 3, z to the power of minus n. And expand this summation. So you will get, actually this one is, this is coming from a z to the power of minus 0. Okay, because we start with 0. So z to the power of minus 0 is 1, right? Z to the power of minus 1, z to the power of minus 2, up to z to the power of minus 3. And if you factorize it, bring out that z to the power of minus 3 here, because this is the highest negative power. Okay, bring it out. So then you will get everything on a positive power inside that bracket. Okay, then you can bring this down. So bring that down. So z to the power of minus 3, 2, and this is 1, this is power of 0. Divide z to the power of 3. So what is the ROC? ROC is a region of convergence. We need to find out what are the z values that give you hz, which is not infinity. So that one is a ROC. So to converge, z can take any value. Okay, any value. So you can use any value except z equals to 0. Okay, what happens if z equals to 0? The denominator, this one, this denominator will becomes 0. Then something divided by 0, it becomes infinity. So only that value, only that value. The rest, whatever you put it there, so you'll get some value. So even if a z is infinity, you put it here infinity, right? So the rest will be infinity. Then at the end, it becomes 1. Okay, close to 1. So then it's not a problem, even though it is even the z is equals to infinity. The problem is only if z equals to 0. So it will give us hz, this hz equals to 0. So that's what is the ROC. So the ROC is thus the ROC is a right-sided, where z is supposed to be greater than 0. So what is a z greater than 0 means all values except 0. Except 0. Only at this one dot, so the value becomes infinity. So the rest is actually not infinity. Okay. And this is example 6. So when we are looking at this one, so this is actually a non-causal. So how do you know this is non-causal? Because now you can do, actually there are 3 methods on how to test stability and causality. So one of it is you can check the impulse response. So what is Hn? Hn is impulse response. Okay, so let's look back at our mapping on causality. So this is a causality. Hopefully you can see it because this is a bit small. Hn supposed to be 0 for n less than 0. So this is the rules. This is the rules if we want to have a causal system. If we are looking at Hn. Okay, because now we have Hn. So this is Hn. And this is n equals to 0. Automatically, we know that this is n equals to minus 1, minus 2, minus 3, minus 4. So it means that Hn is not 0 for n less than 0. So we can conclude that actually this is not causal. So let's see on ROC. So the ROC should show non-causality also. Right, so okay, just put it into the equation, very simple. So this is, we know that this is a minus 4. So starting from minus 4 until 1, because this is 0. So it doesn't count. Okay, if you put it into equation, you get 0 also at the end. So n minus 4 up to minus 1, z to the power of minus n, then you will get z to the power of 4, and then this is power 3, power of 2, power of 1. So, and then if we analyze this, to converge, z can take any value except z equals to infinity. Okay, because if z equals to infinity here, z to the power of infinity to the power of 4, then for sure that one is an infinity. Okay. Can we have a 0 value? Yes, we can have a 0 value, because if this is 0, 0, 0, 0, then hz becomes 0. And 0 is not infinity. So it is a value. Okay, so that's why this hn, this impulse response, so we can have, this is actually the hz, and the ROC, is the ROC. So the ROC is left-sided, where z is actually less than infinity. Okay, so of course you sketch this thing very similar to this one, because it is just on one dot. So this is actually very far away that infinity, right? So to make it simple, actually the sketch is the same, looks the same, but when you write it, it's supposed to be something like this, z less than infinity. I let you to look into this one because this is a mix. So we have some part of it is, at this part, this is supposed to be a causal part. At this part, it is a non-causal part. But combination of a causal and non-causal, it becomes non-causal. Okay, because you cannot have a mix. So if you have a mix, it becomes non-causal. Okay, so look at the example and see. So how can you understand the example? So as a conclusion, ROC of an FIR system, so this is FIR system, is the entire Z plane, except at either 0 or infinity. Okay, so this is for FIR. If we already know that our system is FIR, so the infinity value should be only either at 0 or infinity, or both. Okay, the rest, actually we are very, very safe. So we are very safe. So we have everything on. The rest, except 0 and infinity, everything you will have a value, which is not infinity. Okay, let's try to do this. Let's try to do one of this. Let's do this together. Let's see, now is 10:29. Okay, I'll let you to do number 11. Try number 11, where hn is alpha n minus 5 un. So what is this? This is FIR or IIR? Someone, please. FIR or IIR? Number 11. Please wake up.
IIR.
IIR, yes, true. Very good. Okay. So try to find the HZ. Find HZ. So let's do this. Find HZ. So HZ must come with ROC. So you need to find what is the ROC also. And try to sketch the ROC. Okay. Find HZ together with ROC and sketch the ROC. And this is quite a popular questions actually in test and exam. Okay, so don't make sure you know how to do this. Normally it will be in test and exam, so you cannot miss this. So that kind of question is actually is like is a master question. Okay, I'll give you another 1 minute. 1 minute how to solve that. Okay, finish. Can you guys do it? So any problem? So okay, let's do this together. Okay, hopefully you do it. Okay, because it will be very effective if you do it. Okay, and I will show you how to do it. Okay, let's write that again. What is a HN? So what is a HN? Again, HN is, this is impulse response. Okay, before that, can we do HZ or Z transform to input signal? Can we do that? So normally all the example is actually on impulse response. Can we do Z transform to input signal or output signal? So what do you think? So please answer yes or no.
No. Can you repeat the question?
Can we do Z transform to input signal, which is the XN or YN? YN is output. What do you think?
We can only do on HN.
So is that answer no?
Yeah, no.
Okay, let's see some other response. Please put it on the chat section. So I want to see at least 4 or 5 answer, yes or no. Okay, one already answer. A no. How about the rest? Okay, no. No. Anyone say yes? I want to see someone say yes. And you need to know what is the answer. Okay, no, no, no. Okay, another one. So that we will have 5. So who will be brave to answer it? One more. Come on, wake up.
Yes, Doctor.
Okay, no. 1, 2, 3, yes. All right. So only one person says yes. The rest says no. Actually, the answer is yes. You can do Z transform. Actually, Z transform is done on a sequence, right? HN is actually a sequence.
Sequence is input. Sequence is an input and output, Doctor. It's a process,
okay,
right?
Okay. Let's see, because this is quite an important concept, right? So what is a sequence? A sequence is a value, right? Sequence is a value. It's a value, so it's like it's a series of values. So that is actually a sequence. So it's like you have a one value, and then you have another value, and then another value, right? And
Yeah.
when you put it such that, and then it has index. So this is where, if you look at HN, so yes, we can say that this is HN. HN is actually a sequence. How about XN and YN? Actually,
They are
these two
sequences.
are also sequence.
I see.
And yes, so it's just that. So that's why this is, everyone needs to be very, very clear on this. All of these 3 are sequence. But what is the difference? XN and YN is a signal, but HN is a system. Okay, so do not confuse with that, because in maths everything is just a sequence, but in DSP HN is a system and XN and YN is a signal. Okay, signal and system is for DSP, it's not for maths. So this is where the DSP comes in, the concept. But on maths, they see it, everything the same. It's just a sequence. It's just a sequence. So, and Z transform is actually done on sequence. Okay. I hope you remember that last time I'm saying that a Z transform, a Laplace transform, a Fourier transform, it doesn't start with DSP. those actually start with maths. Okay, so maths people invented it. It's not a DSP person. So okay, so then the answer is yes, xn, yn, we can do Z transform. We can do that. And actually it is done on a sequence, which is the input and output, but a very special for LTI system. Okay, only for LTI system. The system can be represented by a sequence. Okay, which is what we call impulse response. If it's not LTI system, right? If it's not LTI system, it's not linear, it's not time invariant. So we cannot represent the system with HN, the impulse response. Cannot represent it with impulse response. We cannot represent it with a sequence. So that is why LTI system becomes very special. It's we can manipulate this sequence so easy, and then we can optimize the system so much. Okay, so that's why as much as possible. So hopefully anything that we are trying to design to process this signal process, digital signal processing, digital signal. So hopefully we can use LTI because a lot of things can be optimized because the system can be represented as a sequence. Okay, so hopefully you get that concept. Let's get back to our example here. So now I'm going to remove this. Okay, so our HN is, let me write that again. HN is equals to alpha n minus 5 UN. Okay, let's clear a bit on that one. So, okay, from there, so we know that what is a Hz? Hz is a summation of n generally from minus infinity up to infinity of our Hn, z to the power of minus n. Okay, and from there we can get that because we have a un here. So what is un? Un is we have a range from 0 up to infinity. Then, so you can do 0 up to infinity of the alpha n minus 5 z minus n. Okay, you doesn't have to write the un anymore because this un will actually describe the range. So what is the range? The range is from 0 up to infinity. So this is what we get, and then we can expand that. This is actually alpha n multiplied by alpha minus 5 z minus n. And this is actually a fixed value. Okay, because it doesn't have any variable. So this is a variable, which is n. This is a variable, and this is a fixed value. So any fixed value, you can bring it out. Infinity, then you'll have alpha n z to the power of minus n. And then this one, so then we can have our, what we call a common ratio. So what is the common ratio? So it is alpha z to the power of minus 1 to the power of n. So from this common ratio, we will determine the ROC later. Okay, and then we can get that. So if you remember, the formula will be, this is alpha to the power of minus 5, and then multiply with 1 minus alpha z to the power of minus 1 to the power of infinity plus 1 divided by 1 minus alpha z minus 1. Okay, so you should see that. And then, so because this is alpha z to the power of minus 1 to the power of infinity plus 1, so we need to make sure that this alpha z to the power of -1 is supposed to, this alpha z to the power of -1 supposed to be less than 1. So this is where we will get our ROC, which is a z supposed to be greater than alpha. Okay, you do some manipulation on this one. So this is actually z to the power of -1. This is alpha over z, and then z, bring it here. Then you'll get z greater than alpha. So we already have our ROC. And then, so this is where we can finalize. Oops, sometimes that happens. So we can finalize this as a alpha to the power of -5 of 1 divides 1 minus alpha z to the power of -1, where ROC is z greater than alpha. Okay, so this is your final answer. It's supposed to be your final answer. So alpha to the power of -5, and then divide by 1 minus alpha z minus 1. And it's very important you write it the ROC, so which is a z greater than alpha. And if you want to sketch, so this is a real axis, this is the imaginary axis. So, and then because a z is actually a complex value, and then when you have absolute value of z, so this is actually, so what is this? So this is a absolute value of z means radius. Okay, so you should have some radius. What is the radius? We should look at alpha. So let's say alpha is somewhere there, and that's the radius of that z. Okay, what is the radius? The radius is alpha. So then the rest of this, because this is a greater than, so this is actually the ROC. Okay, did you get the same answer? So hopefully you get this thing. So if not, look at it back and then try to understand. Make sure you do a lot of exercise. Even in this quiz one, we have 1, 2, 3 up to 13. Actually, not 13. So we have up to 20 questions. So make sure you do it. And not only this one, if you go to e-learning, so you can see a lot of past questions. So there's a lot of past exam question and even the test question. Okay, the test question is not as much as a final exam, but there's some set of past year test questions. Okay, you need to do that. Okay, so next we will go for stability, because when we are looking at ROC, we can check stability and causality. So we have done causality. So what is a causality? Your ROC must be greater than. So if you see the ROC is greater than, then so we can say that our system is actually causal. So how about stability? For a stable system, unit circle must be inside the ROC. So what is a unit circle? Again, a circle is a circle. So this is a circle. Because why we are looking at a circle? Because a z, when you have an absolute value, it is a radius. Yeah, we have discussed that. So we are looking at a radius. So then and unit circle is where the radius is equals to 1. So what is this? Unit circle. The r is equals to 1. Okay, or what is that? Z absolute value is equals to 1. So let's say this is the unit circle, because you can see that this is 1, so this is always 1. This is also 1. What is 1? Radius. Radius 1. So this is a unit circle. So we are always looking at unit circle. So to check whether the system is causal, stable or not stable. So first you need to have your ROC. So let's say this is what is the ROC? This is wrong. Okay, so this is actually what is the ROC for this one? This one ROC is Z greater than alpha. Okay, so those with lines is actually the ROC, and this is actually described by Z or the R radius greater than alpha, because this is alpha. So this is alpha. So then we check what is the unit circle. If the unit circle is inside the ROC, so in this case, this is inside the ROC. And how we can get that? So we need to make sure that that alpha must be less than 1. Okay, so if the alpha is less than 1, then of course we can say that the unit circle is inside the ROC. Then the system is stable. So if the ROC, if the alpha is greater than 1, so this is one example. So let's say we have, this is the ROC. So what is the ROC? So this is a Z, let's say greater than 2. So this is 2. 2 is here. Okay, same thing. This is also 2. What is this? So this is negative 2. Because after you convert it into radius, it becomes 2. Okay, but on that coordinate, so it is actually minus 2. And this is also minus 2. So where is the unit circle? The unit circle is supposed to be here. So this is the unit circle, and this unit circle is not within the ROC. So then this is actually not stable. Only if the unit circle is inside the ROC, the system is stable. And we have seen that ROC, we can only have 3 types of ROC. Either it is exterior, this one, greater than. This is interior, where you have your ROC less than. And this is a combination of these two. You have a greater than and less than, so you get a ring. Okay, so whatever it is, so you need to make sure that the unit circle is inside the ROC. Then your system is stable. So what is the conclusion? The conclusion is this is actually the third method on checking stability and causality. And checking the stability and causality in Z domain is by checking the ROC. Okay, so causality, ROC must be greater than. Stability, unit circle must be inside ROC. Okay, so any questions? Any question before we go to this one? And of course, you can do this again. All these questions from 1 up to 20. Then you can check. Every time you get a ROC, so will it be stable or not stable? Okay, let's see one example. So this one, number 1. So number 1 is, obviously, this is FIR. Okay, because you can count 1, 2, 3, 4, 5 samples. Okay, so, and we know that this is not causal, but is it stable? And by looking at HN, impulse response, if you still remember, so stability test on HN, you just sum everything. So it's supposed to be less than infinity. And if we check this one, so this is actually if you sum 1 plus 1, 2, 2 plus 2, 4, 4 plus 3, 7. Obviously, this is stable. But you can have a check also in Z domain by looking at the ROC. So whether the ROC actually including unit circle or not. And FIR, so we have a conclusion for FIR. ROC of an FIR system is the entire Z plane, except Z equals to 0 or Z equals to infinity. So what does that mean? The unit circle is always inside the ROC. So for FIR, unit circle is always inside the ROC. So that's another advantage of FIR system actually. So FIR system is actually confirmed always stable. Okay, the one which is there's a possibility of not being not stable is actually IIR. So this is another thing. When we design, normally we will go for FIR system first. So if let's say IIR system have a more advantage, then we go for FIR. We go for IIR. So if not, a simpler system supposed to be FIR because it is always stable. It is always stable, right? So we just need to make sure that whether the system is causal or not causal. Linearity already linear, time invariant already time invariant, stability already stable. So we just need to make sure causality only for FIR. Okay, so we will cover just a little bit. Okay, so hopefully we can do that in 10 minutes, okay, or maybe 8 minutes. Okay, so this is another one in Z transform. So we have a poles and zeros. So we call it a poles and zeros. Okay, what is a zeros? Zeros is Z values that causes H Z equals to 0. Poles is a Z values that causes H Z equals to infinity. And to make it simple, so when you have a H Z, so you have what we call a numerator because we always have this thing. So we have a numerator, we have denominator. Okay, that one is wrong. That one is not the numerator. That one is a denominator. Okay, so actually it is a fraction. So there is a upper side, the lower side, or we call it numerator, denominator. So you just need to find actually a zeros. So this is a zeros. Zeros is roots of numerator. And poles is actually just roots of denominator. Okay, so that's actually in maths. So that's what it means. So whenever you have HZ, so you find roots for the numerator, you get your zeros. You find roots for denominator, you'll get your poles. So, and today we're just going to look on how to get the poles and zeros only. So how to use this and why we need this. So that one is later, not today. Okay, today we're just going to see how to get those things. Okay, so let's see. So this is going to be our last example today. We will try to find out what is the poles and zeros of this system. And actually, this is the same example. So you just need to see how to get the poles and zeros. So Hn equals to alpha n un. So this is infinite impulse response, right? And then do Hz. So we have done this. So you will get 1 over 1 minus alpha z to the power of minus 1. And the ROC is actually z greater than alpha. And when you sketch this z plane, so it's supposed to be something like this. So you put the lines on ROC. So, okay, so this is the region of convergence. Means that all this, the Hz value is not infinity. Within this circle, that white region, the Hz is actually equals to infinity. Okay, so finding poles and zeros are easier when Hz is actually written in a z instead of a z to the power of minus 1. And because we want to find roots. So let's change that. This is to the power of minus power. So we're going to change it into a positive power. So this is 1 over z to the power of minus 1, z minus alpha. Okay, so you bring that z minus 1 out in front. And then do that, you will get z divided by z minus alpha. So what is the zeros again? Zeros is the roots for the numerator. So it means that we just put a z equals to 0 because we have only 1 here, z. Then you just put it equals to 0. Then that is solved. Z equals to 0. Okay. What is poles? Poles is actually roots for the denominator. So what is our denominator? Z minus alpha. So then z minus alpha is equals to 0. Then z is actually equals to alpha. Okay. So in our system, this system, so which is represented by Hn, the alpha and un in time domain. So this is in time domain. So how do we know this is in time domain? Because we have a time bracket. Inside the time bracket is n. then it is a time domain. And how do we know this is a Z domain? Because in that bracket, it is Z. Okay, so then we finish. So what is the zeros? Zeros is Z equals to 0. 1, 0. 1 root. Okay, so we have 1 root only. And we have a 1 root also for poles. And this is how we sketch the poles and 0. So we have a 1, 0 at 0. Okay, so this is 0. And we have 1 pole at alpha. And if you notice, we're supposed to have a real and imaginary value. But in our case here, it happened that our Z, it only has a real value. Okay, because it is possible that you will have a Z equals to, let's say, 2 plus a 3J. Okay, this is possible because actually Z is a complex value. It is a complex value. But in this example, it just happened that Z only has a real value. So that's why when we do the plotting, so this is the real axis. So we are putting a cross at that one. So what does it mean? The imaginary value is 0. Okay, so this is actually equals to alpha plus 0J. Okay, and of course, this is also 0 plus 0J. Okay. For poles, we put a cross. For zeros, we put a circle, small circle. Okay, so we will stop here. Next week, we will see more examples. So we will see more examples because we need to do an inverse. When we do an inverse, so we will deal with this poles and zero again, and we will see more examples. Okay, this is actually a very simple example. Okay, any questions before we end our class today? Okay, so I think there's no question. So any question you can ask me, whether in a WhatsApp or email or any medium that you can contact me. Okay. All right. So that's all for today. So see you guys again next week.
Any attendance?
Attendance always using the link given in the e-learning. Okay. Use that one. So we have only one form. All right. Is that clear? Go to e-learning and click that link. So there is a one link for attendance. All right, so, okay, thank you, everybody. See you guys again next week. Assalamualaikum warahmatullahi wabarakatuh and good morning.
Terima kasih, Doktor. Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam, Doctor. Thank you so much.